Hello students, the next experiment is a measurement of susceptibility of a liquid or a solution by Quincke tube method. The objective of this experiment is to determine the magnetic susceptibility of a given paramagnetic solution for a specific concentration, and then to calculate the mass susceptibility, molar susceptibility, and Curie constant. In order to understand the magnetic susceptibility, we should know what is magnetization. So magnetization, or capital M, is magnetic dipole moment per unit volume. For most of the materials, the magnetization is proportional to the magnetic field. This proportionality holds when the magnetic field is not too strong. So we can say that capital M, that is magnetization, is equal to chi some constant multiplied by capital H, that is magnetic field. So M is equal to chi H. Here chi is the constant part, constant of the proportionality. It is called the magnetic susceptibility. Okay. So those materials that obey this equation, that is M is equal to chi H, that materials are called linear media. And the materials which does not obey this material are nonlinear. Now we know the relation between B and H, right? So H equals to 1 by mu 0 into B minus M, where mu 0 is the permeability in space. So from this equation we can say B equal to mu 0 into H plus M. You can see the equation. Now M is equal to chi H, so B can be, we can say that B is equal to mu 0 into 1 plus chi into H, or in short we say B is equal to mu H. So what is mu? Mu is equal to mu 0 into 1 plus chi. So this is the relation between permeability and magnetic susceptibility. Okay. Now relative permeability, that is mu r, is equal to mu by mu 0, right? So relative permeability is basically 1 plus chi. So mu r, that is relative permeability, is 1 plus chi. This is the relations. So all magnetic materials can be classified according to their magnetic properties into three major groups. First, diamagnetic, second, paramagnetic, and third, ferromagnetic materials. So what is diamagnetism? Depending upon the value of chi, this can be classified. So when chi less than 0, that is the value of chi is negative and it has a very low value. So we can say that modulus of chi is very less than 1. So that materials can be called as diamagnetic materials. So copper, bismuth, etc. These are the diamagnetic materials. So what is the origin of the diamagnetism in a substance? It comes due to the change in orbital motion of the atomic electrons. Okay, so when magnetic field is applied, So there is a change in the orbital motion of the atomic electrons. Okay, so that is the main cause of the diamagnetism, right? So for paramagnetism, the value of chi is greater than 0, but the value is very low. Okay, so for both diamagnetism and paramagnetism, the value of chi, the magnetic susceptibility, the value was very small, very low value. But for paramagnetism, it is positive, and for diamagnetism, it is negative. That is the difference. So in the picture, you can see the M and H graph is basically linear, both for paramagnetic and diamagnetic material, right? But the difference is the slope are positive for paramagnetic material, and that is negative, the slope is negative for diamagnetic material. So paramagnetic material is ferric chloride, MnSO4, platinum, etc. Paramagnetism, the origin of paramagnetism is the existence of permanent dipole moments. Okay. So for paramagnetic materials, the substances, the atoms of the substances have permanent dipole moments. And when the magnetic field is imposed on the material, these dipoles are aligned according to the magnetic field. Okay, so this is the origin of paramagnetism. Now move to ferromagnetic material. So ferromagnetic material, the value of chi is many greater than 1. That is, it has a large value. It has the large value, and the value must be positive. Okay. So the example is very common: iron, cobalt, nickel, steel, that are the ferromagnetic material. The properties and the origin of ferromagnetism will will discuss in the later experiments. So there are two ways to measure the magnetic susceptibility. One is force method and the other is induction method. Here in this experiment, Quincke's method is the former one. That is, it is a force method. Okay. So suppose the material of permeability mu is placed in a magnetic field through this tube. So Quincke's tube is a specially designed tube. You can see in this picture that here one arm is capillary one, right? And the other arm has a greater diameter. And the material is taken in this experiment is MnSO4 solution. Okay. So suppose the solution has a permeability mu and it is placed in air. So surrounding material, the permeability of the surrounding material is mu A. Okay. Now suppose the surrounding medium, that is air, here it is air, it is suppose evacuated. Okay. Then what would be the potential energy? The potential energy would be mu into capital H square into the volume by 2. Here the volume of the materials under the magnetic field is taken as V. Okay. So the potential energy would be mu H square V by 2. As the energy, we know that it is half into integral of H dot B into dV. Okay. So from here the potential energy can be said. Now, since the body, since the material, the medium, here it is the solution. Okay, uh, it replaces the surrounding material, that is air, whose potential energy would be mu a h square into v by 2, right? So what would be the total change in the potential energy? The change would be minus, because the potential energy was minus, right? So minus mu a h square v by 2. Then what will be the force? So we are taking the force in the x direction. What is x direction? Along the tube, right? So the materials can only move in the along the x direction, that is the along the arm, along the capillary arm. Okay, so it is taken as x direction. So what will be the force in this x direction to move the material? That would be minus of derivative of the potential energy. So here we take is as fx, that is equal to minus ddx of a minus of mu minus mu a into h square v by 2, right? So now what is the what I have already told, that the relation of mu and chi, right? We discussed about the relation of mu and chi, that is mu is equal to mu 0 into 1 plus chi, right? So in terms of chi, we can rewrite the equation as fx is equal to half mu 0 chi minus chi a into v ddx of h square, right? So if the volume, if the small volume we are taking as dv and the length is dx, okay, so we are taking dx as the length, as a small length, and the cross section is capital A, okay. So in terms of dv we can write a into dx. So the total force, the change in force, the differential force dfx would be half into mu 0 chi minus chi a into a ddx of h square dx, right? So the total vertical force along the liquid column, that is we are taking in the whole region under the magnetic field, the total force would be half into mu 0 a into chi minus chi a multiplied by h square minus h0 square. So what is h? H is the magnetic field which is subjected to the magnetic subjected to the that poles, okay, which are covered in that poles, that is the magnetic field H, and H0 is the magnetic field which is weaker, which is smaller, that is for the lower part of the limb, okay, lower part of the capillary limb, narrow limb, okay. So under the magnetic field, the vertical force that will tend the material to rise for the paramagnetic material, and that force is half mu 0 a chi minus chi a into h square minus h0 square, okay. Now if the solution has the density rho, and we are taking this density of the air is rho a, Then change in force in the liquid as the liquid rises a height of h, small h. It would be rho minus rho a into gh into capital A. Capital A is the cross section area, right? So these two forces must be equal in equilibrium, right? So these two forces, which I've already discussed, due to the magnetic field, the forces, and due to the height change, due to the rises of the liquid of the solutions, these changes in the force, that force, two force must equal. So we can say that rho minus rho a into gh capital A is equal to half into mu 0 capital A into chi minus chi a into h square minus h0 square. Okay, now h0 square, it can be negligible because with respect to capital H, h0 is much more smaller, right? Chi a, that can be also ignored, and we can also ignore the density of the air. Okay, so after this neglecting of rho a, chi a and h0 square, we get this relation as a chi is equal to 2 rho gh over mu 0 into capital H square, right? So here is the relation that we will use in this experiment. Now moving to the experimental part. So in this picture you can see a digital Gauss meter, a constant current power supply, a traveling microscope, and electromagnet and Quincke tube with the stand. So if we connect the constant power supply with the electromagnet, then when we increase the current, corresponding to that, magnetic field will be increased. Okay, now the Quincke tube with the stand, that is the solution, it is placed in between the two poles of the electromagnet. Okay, in the middle of the two poles of the electromagnet, and as it is the paramagnetic substance, the response, the height response will be very weak. The uh, rise in height will be very small, as the response in the magnetic and the magnetic response will be very weak, right? So we'll use the traveling microscope to measure the height, to measure the rise in the height, the change in the height. Okay, and we'll use the digital Gauss meter to find the magnetic field at a particular current. Okay, so we'll see the detailed operations of the apparatus in the demonstration, in the practical demonstration. So there are four parts in the experiment. Firstly, the preparation of the solution and determination of the density of the solution. Okay, so we have to prepare the solution in a beaker. So mass of the beaker is termed as mb. Mass of the beaker and the water, that is mbw. Mass of the beaker plus water plus salt, that is mbws. Okay, so we'll measure these values. Okay, we'll measure the mass of the beaker plus water, and mass of the beaker plus water plus salt. Then we can calculate the mass of the water and the mass of the dissolved salt, right? So these masses we'll use to calculate the values. Okay, that we'll see later on. Now move to the determination of the density. So mass of the specific gravity bottle, there is a specific gravity bottle in the lab. So the mass of the specific gravity bottle, it is termed as W1. Then mass of the specific bottle, and we'll put water in this bottle. The total mass would be W3. And we'll then put the solutions in the specific gravity bottle, and the total masses, that is the masses of the specific gravity bottle and the masses of the solution, the total solution is termed as W2. So from W1, W2 and W3, the density of the solution can be determined using this relation: rho is equal to rho water, W2 minus W1 over W3 minus W1. So the rho water can be taken as 1. So the relation is now rho is equal to W2 minus W1 over W3 minus W1. Thus the density is measured. Okay. The second part is the calibration of magnetic field as a function of magnetizing current. So why this calibration is needed? Because at a particular time, at a same point of time, we cannot use the digital gauge meter and the Quincke tube in the magnetic field, right? So we'll first calibrate the magnetic field as a function of magnetizing current, and then we'll remove the probe of the digital gauge meter and put the solutions in the magnetic material. Put the solutions of the magnetic material in the magnetic field, and we'll increase the current. We'll have the magnetic field corresponding to that current from the graph of the calibration. Okay, so we'll calibrate the magnetic field as a function of magnetizing current, and then we'll plot it, and it will be a straight line, and from this graph we'll use the value of magnetic field at a particular current. Okay, then we should note the room temperature in Kelvin, and finally we have to measure the rise of the solution level, that is the rise is called H, with the help of the traveling microscope, and as a function of magnetic field, we have to plot it. We have to plot a graph small h as a function of h square, the magnetic field square. Okay, so we'll increase the current, and we'll observe the rise in the solution level, and will correspond to that current from the calibration. We'll have the value of the magnetic field corresponding to that particular current. So we'll use we'll plot the graph of small h, that is the rise in the solution level, as a function of capital H square, and from the relation we have already discussed, that is chi is equal to 2 rho g h by mu 0 h square, then it will be a linear equation. If I plot small h as a function of capital H square, then from the slope we can have the value of chi if we put the value of rho, g and mu 0. Okay, now chi 0 is the mass susceptibility, that is chi over rho. Okay, and molar susceptibility we can measure from the relation molar susceptibility, that is chi double prime, is equal to chi prime, that is the mass susceptibility, multiplied by the molecular weight. Okay, and finally the Curie constant we can have from the relation chi is equal to c by t, as the value of as the chi is inversely proportional to capital T. From we have already read it in the Curie's law. So here capital C is the Curie constant. Okay. So after getting the value of chi, we can calculate chi prime, that is mass susceptibility, chi double prime, that is molar susceptibility, and the Curie constant if I know the capital T, that is the temperature. Okay. Now there must be a correction, because there is water in the solution, right? So the diamagnetic contribution of the water, it should be corrected. So the total susceptibility of the solution, it is the susceptibility of the salt plus the susceptibility of the water. Okay. Now the mass susceptibility chi prime is equal to ms by ms plus mw, that is the mass of the dissolved salt. Ms is the mass of the dissolved salt, and mw is the mass of the water. So ms over ms plus mw into chi prime chi prime of the salt, that is mass susceptibility of the salt, plus mw over ms plus mw multiplied by the mass susceptibility of the water. Okay, so from here, if we know the value of chi prime water, that is the uh, mass susceptibility of the water, it has very standard value, right? So after putting the value of chi prime water, we can have the value of chi prime salt. If we put chi prime in this place, and have already if we know the value of ms mw and chi prime we can calculate, and then putting the value of chi prime water, we can have the value of chi prime salt. Okay, so here this correction should be incorporated with the results. Okay, so these are the things for this experiment. So we'll see you in the live demonstration. Thank you.